Hey there, Math 2403. Here we are, Unit 2, video number 2. We'll be continuing to talk about probability. We'll learn the basic rules of probability, and we'll talk about an interesting situation where you have at least probabilities. Let's get right to it. So let's talk about the probability rules or axioms. They're fairly basic. I think we pretty much will understand most of these just by common sense in a way. The probability that you have something that's impossible should be 0, and the probability that something is certain should be 1 or 100%, and all other probabilities should be in that range. So probability is always bounded between 0 and 1 for any event. So those are the three, fundamental basics of probability. Then we can build some other rules from there. We can build the rule for complements. Suppose I have an event A. I'll denote the opposite of it with A bar. I know that that's a little confusing because we used X bar to mean the mean. Sometimes you'll see people use A with a superscript C for A complement. But it's pretty common to see this bar notation in set theory. So I thought I should, keep you aware of that. The rule of complements is pretty obvious. The probability of something happening plus the probability that it doesn't happen has to equal 100%. Everything happens or doesn't happen. These two probabilities don't have to be equal to one another. It's not 1/2 plus 1/2. Maybe A has a 1/5 chance of happening, then A not happening would be, say, 4/5. So everything plus its opposite would have to equal 1. There's a Venn diagram here that didn't turn out super great, where we try to use area to kind of help us visualize probability. Suppose I have everything that can happen. I have this rectangle here with an area that equals 1 or 100%. Here's my whole universe. It's everything that can happen. Then I'll denote the probability of A occurring as the area of this circle. Well, then the probability of not A is everything on the outside of that circle. So if I take everything that's inside the circle and I add it to everything that's outside the circle, I get the whole area of the block, which is 100% or 1. So sometimes that's called an area diagram. It turns out that a lot of times it's hard to calculate the probability of something, but it's easier to find the probability of its opposite or complement. So we can take advantage of this equation and rearrange it. If you want to know the probability that A happens, you can just do 1 minus the probability that it doesn't. So we'll use that complement rule quite a bit, where the complement is easier to find than the trying to solve something directly. This particularly will happen when we have situations of or, where you have the probability of A or B or C or D. That's difficult to calculate directly. It's much easier to figure out the opposite of that. We'll see a fun example of that when we get to this birthday problem that's coming up. It's sort of a neat example. Somewhat counterintuitive, actually, but pretty neat. We can do a few examples here, just using some of these ideas. We haven't done a lot of examples of actually calculating probability yet, so let's do one here. We have, in samples of size n equals 10 of these transmission housings, we inspect them, and we get asked, what's the probability of not having any defectives during one of those inspections? So maybe we should define that, a variable x is number of defectives in a group of 10. Like we're looking at 10 of these things. What's the probability of having none? So what's the probability that our x equals 0? No defectives. Well, we need them in that case maybe to, instead of saying, I could say not defective, not defective, not defective, not defective. I need them all to not be defective, otherwise known as good. They give us a probability in here that over time they know that the defective ones occur at a rate of 6%. So on average, your probability of being defective is 6%. But in order to get 0 defectives, we need them all to be good. So basically, I'm going to need a good and a good and a good and a good, well, 10. Well, what's the probability of being good? That's the probability of not being defective. So we're using that rule of complements here. That will be 1 minus 0.06. So there's a 94% chance that they're not defective or good. So we would just take that 0.94 and multiply it by 0.94, etc., and so on. Each one of these is a good one or not defective. They're independent of one another. We'll assume that if the first one's defective, it doesn't change the probability of the next one being defective. I think we can say that because of this long run 6%. We'll just assume that we're picking these at random in such a way that you might consider in real life 2 in a row, they might have some sort of dependence on one another. But in this case, let's make the assumption that they don't. I'm just multiplying 0.94 10 times, so I can write it as 0.94 to the 10th. The probability of that then ends up being 0.538. I would have had a hard time just guessing the answer to that, actually. That's one of the hardest parts of probability, is gaining some sort of number sense. It feels like it could be okay, but I mean, if you just asked me to guess beforehand, I might not have said it was around 50%. So we have to sort of trust the rules and axioms so that otherwise we really have no idea what our answer might be. I multiplied these things because I basically applied the counting rule that we had. Remember, if we wanted to know the number of ways of arranging something, we multiplied n1 times n2 times n3 times n4 to find the total number of ways. We do a similar thing with probability here, where we just multiply our ands together, which we'll see in an actual rule in a second. A couple's going to have 3 kids. What's the probability that they have exactly 2 boys? Let's assume that boys and girls are equally likely. I'm not sure that they actually are. I think maybe girls are slightly more likely, but it's, very slight. So I think we're okay to a couple decimal places anyway to make that assumption. Let's do this example by listing out all the things that can happen. And one way you can do that is to use a tree diagram, when you have a small number. With the 3 kids example, I think we can list out all the possibilities. Of course, if we generalize this to be, you had 20 kids and you wanted exactly 8 boys, it would be significantly harder because we couldn't just list it all out like we're about to do. Here we are, we could have a boy or we could have a girl on our first kid. Once we have a boy, we could get another boy or we could get our first girl. After having 2 boys, we could get boy number 3 or girl number 1. And we can just keep doing this. It's a nice systematic way to show all the possible outcomes where you don't miss any. And when you're done with this, you can see how many possible outcomes there are. You can just follow the branches. You can have boy, boy, boy. That's one possible family of 3 kids. Or boy, boy, girl. Or boy, girl, boy. Boy, girl, girl. Girl, boy, boy. So I say there are 8 different ways to have 3 kids. They're listed here. This is called the sample space. It's all the possibilities. So to figure out the probability of exactly 2 boys, we just have to count all the ones that have exactly 2 boys. So there's 1, 2, 3 out of the total of 8. If I asked what's the probability of exactly 2 girls, we'd also get 3/8, or we'd be in trouble. The world would get out of balance in a hurry. Now, this is a textbook question where, textbooks are a little behind the times, where we define as boy or girl. So my apologies to those who may take issue. Maybe we should delete these from textbooks, but they're such a common example. It felt wrong to not do an example with families, but they are getting dated, certainly. How might we do this, using our counting techniques? It would be tough. I think it'd be pretty easy to say how many families you can have. To get the 8 is not too hard to count. You have 2 choices for your first kid, 2 choices for your second kid, and then 2 choices for your third kid. So that gives a total of 8 ways. But the probability of 2 boys and 1 girl is, or the number of ways of getting 2 boys and 1 girl is a little trickier. Because you can't just use this multiplication rule. We would have to use a factorial rule. If you're trying to find the total number of ways of having, of mixing around 3 things, you'd say there are 3 factorial ways. 3 times 2 times 1. But that only applies if they're distinct. If I swap 2 boys around here, it's still boy, boy, girl. So I'd have to do a little bit of adjustment for that, for the repetition. So the the way to get the 3 is I'd have to say there are 3 factorial ways. And because I need 2 boys who are essentially identical in that they're both boys, I divide by 2 factorial and then 1 factorial. And that will give me 3. It'll be 3 times 2 times 1 over 2 times 1 times 1. And you're left with just 3. So this is the total number of ways of getting 2 boys in 3 kids. And then this is the total number of ways of having 3 kids. So it would be the ratio of those. And then this technique would generalize if you had, 10 kids or something, and you wanted to know the probability of exactly 4 boys. We could use this sort of idea where we wouldn't have to list them all out. Compound events, this is our OR situation where we're going to combine several simple events. I'm going to use this notation. This is from set theory. This U is for union, and it also just means OR. What's the probability of A or B? It's just a sum. It's the probability of A plus the probability of B. And then you need to take away something. You need to take away the case where both are true. This symbol here is the intersection symbol, and it just reads as AND. So the probability of A or B is equal to the probability of A plus the probability of B minus the probability that they both happen simultaneously. Now, that seems a little weird to subtract that. So I drew a little picture here, another one of those Venn diagrams. The box is the whole universe. And remember, if I add the probability of A is everything in my A bubble. And then the probability of B is everything in my B bubble. But you see they overlap. Now, basically the stuff in the intersection there got counted twice. And that's why I subtracted it once. This problem gets quite complicated. I mentioned at the beginning in the intro, if you have more than 2. Even at 3, let me just do a little bit of an aside. If you wanted the probability of A or B or C, it would make sense that it would be the probability of A plus the probability of B plus the probability of C. But you end up with a lot of overlap. Let me just draw a little picture here. Here's my probability of A, here's my probability of B, and here's my probability of C. You notice that this section here got counted in A and B. So I'm going to subtract that because it got counted in both. This shaded section was counted when I did A, and it was counted when I did B. So I'll take it away. Minus the probability of A and B. But there are other problems besides that. If I have A with C, I added this region twice. So I better take it away. And then there's a third problem where we have B with C. This region here got counted twice. So I better take it away. So my formula is getting kind of long here. And the worst part of it all is that this middle section, the very inner part, right here, this inner part was counted in A, it's counted in B, it's counted in C. But it got taken away in each of these pieces. So now it's not even being counted. So I need to add it back in. So you can see how this formula gets really nasty when you get to 4 or 5 or 10 statements. So this is the kind of problem that we will often try to use the complement on. And it will make it a bit easier. It still may be hard, but I think it will be easier than trying to evaluate all of this. But in the 2 option case, it's not too bad. So I think we can handle those. Here's a little example. We're going to draw the top card from a deck. What's the probability that it is red or an ace? So we're only drawing one card. We want to know the probability that is red or it's an ace. I think most of us could probably solve that without the formula, but I'm going to run through the formula just to verify that, give you some confidence that that formula up above works. So the formula says we'd find the probability of a red card, and then we'd find the probability of an ace, and then we subtract the probability that it's both red and an ace. You'll get used to this notation of or and after a little bit. Red cards, I guess there are 26 red cards in a deck out of 52. And remember, I'm just drawing one card here, so my total isn't decreasing when I do this one. What are my chances of getting an ace if I draw one card? Well, there are 4 aces: heart, spade, diamond, club. And we divide that by 52 possibilities. And then we need to take away the probability of having one that is both red and an ace. So 2 of the aces are red, the ace of diamonds and the ace of hearts. So we'll take those away, leaving us with a total of 28 out of 52. No, I think most of us probably could have reasoned that out without the formula. So when you're solving these, you don't necessarily have to list this out. You could jump to the answer, I think. I know that 26 of the cards are red, and then I get to add in 2 more black aces, so that gets me up to 28 out of 52. You don't have to reduce this fraction. I'm very happy seeing fractions like this, because it helps me see where you got the numbers from. So this is going to feel weird to leave an answer that way, but some of you just won't be able to stand it. We've been trained our whole lives to reduce fractions, so you certainly could reduce it. But I really don't mind them like that. Some definitions for you. Whenever you have 2 events that can't occur at the same time, your picture looks like this. The probability of A and the probability of B don't overlap, and therefore their intersection the probability is then 0. And it simplifies the formula up above by a lot. You just have to do, instead of having your formula in the standard way, we can replace this intersection piece with 0, and then you just add your probabilities together. This is called mutually exclusive. Means that 2 events can't occur at the same time. So I'll use that term periodically, so make sure you have a rough idea of just what that means. Mutually exclusive means they can't happen at the same time. And it actually makes things a lot easier. Let's see what happens in this example. We're going to roll a pair of die, list the sample space of all possibilities, and then find the probability of getting a 7 or an 11. So that's a pair of dice. So we're looking for a total of 7 or 11. X equals total on 2 dice. We want the probability of getting a total of 7 or the probability of getting an 11. If we use our formula, we'd say it's the probability of getting 7 or plus the probability of getting 11 minus the probability that both happen. Well, that's a case of something being mutually exclusive. When you roll 2 dice and you figure out the total on them, you can't have a total of 7 and a total of 11 at the same time. So this part is 0. They are mutually exclusive outcomes. So it makes our formula easier. We just need to find the probability of rolling 2 die and getting a 7. And we need to figure out the probability of rolling 2 die and getting 11. And then just add them up. That's maybe easier than it sounds. We need to maybe figure out the chances of getting a 7. And there are many ways of getting 7s. So let's list out all the things that can happen when we roll 2 dice. On your first die, you could get a 1, 2, 3, 4, 5, or 6. And then on the second die, you could get a 1, 2, 3, 4, 5, or 6. This will list, we can figure out all our totals using this nice little chart. If you get a 1 and a 1, your total is 2. A 1 and a 2, your total is 3. And the chart is super easy to fill in because it's a nice pattern here. We can see that there are 36 possibilities when you roll 2 dice. This is a thing that students often get mad about, is that the order of them does matter. When you get a 1, 2, that's different than a 2, 1. And if you don't believe it, you can color the die. Make one of them black and the other one red, and that way you can tell the difference between them. Or roll one die out of your right hand and the other one out of your left, so you can see that 1, 2 is different than 2, 1. So once you're convinced that order does matter here, we can find the probability of getting 7s. There's a whole list of them here. So 1, 2, 3, 4, 5, 6 ways to get a 7. So our answer is 6 out of 36 to get a 7. And then to get 11, there are 2 ways to get 11s. So 2 out of 36. And there's our answer, 8 out of 36. Again, I'm not going to reduce it. I know that some of us are going to have issues with, well, why is there only one way of getting 1, 1? But there's 2 ways of getting 2, 1. Because it's still 1, 1 regardless of which way you turn it around, but it's different 1, 1 versus 2, 1. We can move on to independence next. Independence is a topic that's similar to that mutually exclusive, meaning that it feels like it should have the same meaning, but it's related to when we do something multiple times. So it's, instead of just doing one trial and having the 2 things happening, say, simultaneously, we're going to do multiple trials and see if the outcome of one affects the outcome of the other. If that is true, then the events are dependent. If the outcome of the first one doesn't affect the outcome of the second one, then they're said to be independent. So let's talk about the dependent case. That's where I need some new notation here. I want to find the probability of B happening given that A already occurred. So this notation here, this bar, is just a notation for given, just like we had notation for and or. So we will use this in our dependent cases. The multiplication comes up. We've already actually been using it because it comes directly from the multiplication rule from counting. If you want the probability of A and B, you just do the probability of A times the probability of B. That is, if they're independent. If they're dependent, you find the probability of A first, and then you find the probability of B given that A already happened. We'll see some examples so you can get a feel for what's the difference between those two. Let's talk about coin flipping. What's the probability of getting 2 heads in 2 flips? So we are repeating the experiment. We're doing it twice. We want the probability of 2 heads. So we need a head on our first flip of the coin and then a head on the second flip. Well, that means we need a head on the first one for sure, and we need a head on the second one. It doesn't matter what happened on the first flip, though. Coins don't remember. These are independent events. Sometimes we're superstitious and we start thinking that things are independent when they really aren't. If I flipped a coin 4 times in a row and I got heads each time, I would start to feel like I was due for tails. But the coin doesn't remember that I did get 4 heads on the previous flips. So there is no I'm due for a tail when you have independence. There's one side of a coin that's a head and 2 sides in total, so we get 1/4. Maybe if I could add a question here. What's the probability of a head and a tail in 2 flips? This is a little trickier. I could get a head on the first one and then get a tail. Hey, I don't even need to put subscripts. I could just say, I could get a head and a tail. Or I could get a tail and a head. Right? There's 2 ways that this could happen. So the first, and they're independent. So I can do probability of head times probability of tail plus probability of tail times probability of head. And they're all 1/2. So we actually end up with a total of 1/2, which seems weird that it's easier to get a head and a tail than it is to get 2 heads. But that makes sense if you do think about it. Your options are head head, head tail, tail head, or tail tail. So the probability of getting head head is 1 out of these 4 possibilities. The probability of getting a head and a tail, well, there are 2 different ways it can happen out of the 4, which ends up being 1/2. So watch out for that sometimes the order will matter. If I said what's the probability of getting a head on the first flip and a tail on the second flip, then I wouldn't have to worry about having to do the second case. And then it would match. Each each one of these outcomes is equally likely. They're all 1/4, 1/4, 1/4, 1/4. And if you add them all up, you get 1. Maybe I can write that. That's its probability distribution. The 4 outcomes, the outcomes probabilities, and their total has to equal 1. Sorry, I went off the script there for a second, but it happens. Some people like to play poker. If you're playing Texas Hold'em, you get dealt 2 cards, and that's your hand. And then you use that hand with community cards. Everyone gets happy when they get dealt 2 aces because it's the best starting hand you can have. What are the chances that you actually get dealt 2 aces in 2 cards? So what's the probability of getting an ace on my first card and then an ace on my second card? I need to get an ace on the first card. And then I need to get an ace on my second card, given that I already got one on my first card. So when you're dealing with cards, you start to end up in a dependent situation. Your second card depends on what you received for your first. We'll see it in the numbers here. The probability of getting an ace on your first draw from the deck. Well, there are 4 aces in the deck and 52 total cards. And now when I go to get my second ace, it's a little trickier because I already removed one from the deck. So there are only 3 aces left. And in fact, we also removed a card from the deck, so there's only 51 cards remaining in the deck. So you can see how the second card depends on what happened on the first card. We could calculate this probability. Take out my trusty calculator. I get 0.00452. 5. I rounded that last digit. So roughly 4.5 times in 10,000 hands, or 45 times in 10,000 hands, roughly 4.5 times in 1,000 hands, 10, 100,000. So pretty, remote chance of getting this hand actually. 4 or 5 times per 1,000 hands. If you're playing poker with your friends, it takes a long time to have 1,000 hands. So you get kind of excited when you get this one, because it is, the highest you could start with. It doesn't mean you're going to win. That's for sure. Everyone has a story about how they lost with this hand, if you've ever played any poker. I want to add another one. What are your chances of getting a 9 and a 5? They call that the working man's hand. You work from 9 a.m. to 5 p.m. This one, your order is going to matter. Because you could get, your first card can be 9, and then your second card could be 5. Or you could get your first card as a 5, and then your second card could be a 9. So this is tricky. What are your chances of getting, get a 9 and then get a 5, given that your first card was a 9. And we'd have to do that for the other one here. It's get the 5 times the probability of getting a 9, given that your first card was a 5. I lost some subscripts there. So again, I'm going off the script a little bit, but your chances of getting a 9 are 4 out of 52. And then your chances of getting a 5, well, there's still 4 5s in the deck because you got a 9 on your first one. But there are only 51 cards left in the deck because the 9 was removed. And then the other option was you get a 5 on your first card, and then a 9 on your second card. There's still dependence because you've removed a card from the deck. So that's why the totals are decreasing there. In the other one, both numbers decreased because you're talking about 2 aces in a row. Here you're talking about 2 totally different types of cards. Doing some calculations, your chances of getting this hand are quite a bit better. It's 0.0121. You could leave your answer as a fraction or as a decimal, or you can convert this to percent, whichever form you prefer. I just find that if the fractions are something I can't obviously look at, I often will go to decimal. You know, if it ends up being 1/3, I just leave it as 1/3. But if it ends up being, 743 5,756, then I'm more likely to write the decimal. But they're all just probability. So yeah, your chances of getting this hand are a lot better than your chances of getting the other one. At least situation, this is where we're going to take that rule of complements and take full advantage of it. If you want the probability of at least one success, that means 1 or 2 or 3 or 4 or 5 successes, etc. But the opposite of at least 1 is none. So it's a lot easier to calculate that than try to find the probability of 1 or 2 or 3 or 4 successes and then add all those together. Here's a little example. Find the probability of getting at least one ace if you are given 5 cards. So suppose I let X be my number of aces. I want at least 1, so that means 1 or more. In math notation, that means X is greater than or equal to 1. So in 5 cards, I could get 1 ace, or I could get 2 aces, or I could get 3 aces, or I could get 4 aces, or I can't get 5 aces. There are only 4 in the deck. So I don't have to worry about that situation. I could find the probability of these 4 things and then add them all together. But that will be difficult, especially for the 2 and 3 cases, because there's many ways it can happen. You can have ace, ace, something, 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 or something, ace, something. So you have to figure out all the different ways that you can get, say, 2 aces. So this calculation here requires that you calculate each of these situations. And we're not the best at counting, so I think it would be easier for us to try to find the opposite of this. The opposite of greater than or equal to 1 in math notation will be X less than 1. The opposite of greater than or equal is less than. Notice 1 will always have the equal sign and 1 won't. Well, because you can't get a fractional number of aces, there's no 0.5 aces, I know that I have to have a value of X equals none. And now that's easy to calculate. I'm drawing 5 cards, and I need all 5 to not be aces. So the first card isn't an ace. There are 48 non-aces out of 52 cards. But now the next card depends on the first card. It has to not be an ace as well. But there are only 47 left. And only 51 cards left. And then we can follow the pattern. 46 out of 50, 45 out of 49, and then 44 out of 48. Right now I'm wondering, like, what is this answer going to be? 70%, 20%. It's hard to estimate. Let's see what we do get. Let's just do the whole thing. Punch the whole thing into my calculator here. I get 0.3412. Approximately 34% of the time, if you get dealt a hand of 5 cards, you'll at least have 1 ace in it. So if you're playing poker and 5 card stud, don't get too excited about just having 1 ace, because it happens very frequently. I'm going to do one more example here, similar to this one, maybe less intuitive. It's called the birthday problem. If you all currently have around 25 people in your set, what are the chances that 2 people in your set have the same birthday? Try to estimate it. Take a guess. Is it 50%? Is it 1%? For me, it seems like there are 365 birthdays, and 25 out of those 365 days. So to me, it seems like the probability should be around like 25 divided by 365. So maybe 7%, under 10% chance. That's my guess. But it turns out it's going to work out to be a lot higher. So we're going to ignore leap year, and we're going to assume that every day of the year is equally likely, which may not necessarily be true. Maybe worldwide it's true, but certainly there may be more people born on certain dates, due to, well, whatever factors, holidays or something. We want the probability of having at least one match. A pair of people who have the same birthday. That's hard, really hard to calculate directly. Bill and Steve could have the same birthday. I could have the same birthday as Steve. Steve could have the same birthday as Mary. Jonathan could have the same birthday as Xavier. There are a lot of different ways that you can have a match. Almost too many to count, especially with 25 people. And that's just pairs. It's possible you could have 3 people with the same birthday or 9 people with the same birthday. Sure, it would be low, but it can happen. So let's abort that idea of trying to do it directly and try to do the complement. What's the opposite of having at least one matching pair? It's none. What's the probability of having no one who matches anyone else in the class? Now that's more reasonable because there's only one way. Everyone is different. So we don't have to worry about all the different ways we can mix it up. But it's still a relatively hard thing to grind out on our calculator. Suppose I go first I get to have any birthday I want. I haven't matched anyone. So there's a 365 out of 365 chance I haven't matched anyone. So that's person one. Then we have person number two. Their only rule is they can't match person one. Well, there are 364 birthdays that they get to pick from because one has been used up by me. But there are still 365 days in the year. And then we just keep going. There are 363 birthdays available for person three. Maybe I shouldn't underline these. And then person four has 362 birthdays. And we just keep going until we hit the last person. So 365 minus 25 is 340, but it should be 341, shouldn't it? Like if I had 4 people, I would go 365 minus 4. That would get me to 361, but it's 1 bigger than that. So following that pattern, I think we can do this. We could try to write this into factorial notation, but it's too big for our calculators anyway. It's 365 factorial on the top, almost, because it stops at 341. So I'd have to divide by 340 factorial, and then divide all of that by 365 raised to there were 25 students there, people. These numbers are too big for our little calculators. So you probably have to punch it in, number by number. I'll save you the trouble. I already did it. I thought that this answer was going to be around 6%, but it turns out it's shockingly large. There's over a 50% chance. It's actually 57% with 25 people that you have a match. So get on your communicate with the rest of your set and see if you guys have a matching birthday in your set. There's a pretty good chance that there is one, assuming that you still have 25 people remaining. So this is a great example of using the complement to simplify something. And it's also a great example of how hard probability can be, in that it's hard to, I really didn't expect the number to be that high. So the number theory part or the number sense part can really make things hard for this stuff. But just keep bearing with it. Practice as many problems as you can. And eventually you do get a little more intuitive. But I've been doing this a long time, and it's still pretty hard for me to make some of these estimates. I think that's enough for this one. I'll see you all in the next video, where we will continue on doing a bit more probability. We're going to work more on conditional stuff in the upcoming lecture. So see you there, and have a good one.